Hey guys, it's been a while since I last did one of these. Been a fair few weeks. I looked at it the other day. It's like, oh, it's been a month because I've been pretty busy getting stuff together for a house and other sorted work and other things. But anyway, I do want to continue on this boot sector thing we're doing here. So, like I said, I left off here, and we're gonna try to load past the first 512 bytes in our file. So that's what I'm going to do. We're going to use a thing called cylinder head sector addressing, and we're going to use BIOS Interrupt 13, AH2, and later on we can use AH3, which will write data, but we're doing Interrupt 13, AH2, which will read data from our disk, well, our virtual disk here, because we are emulating, but our disk into memory, to our working RAM, is what we're going to do. Cylinder head sector addressing brought to you by our good friend Wikipedia, always trustful, reliable source. But in this case it is. Basically, if you can think of a mechanical hard drive, if people still know what that is with all the flash storage and SSDs flying around these days. Mechanical hard drive or an old floppy disk, you have one like magnetic disk, right, which they show here. And you can have multiple ones stacked up. They're called platters. Back in the day, they were called tracks or heads. And that's where the head part of cylinder head sector addressing is. But basically, you take all the platters stacked up on each other. Maybe you can think of it like a stack of CDs, if you even know what that is. The full thing by itself, is a big circle. It's a big cylinder. So if you bisect or cut out like a circle, like a tree ring, out of that stack of CDs or the platters in your mechanical hard drive, that's known as a cylinder. And then if you section off parts of the cylinder here, parts of the cylinder, or the track it's called as well, but parts of it, you get a sector that the read-write head will read at a time. And then each platter itself is called a head. You have two sides to the head, and that's why you have multiple read-write heads, well, for the disk. The disk itself has its heads, and it can read-write on either, the top or the bottom surface here in between. But cylinder head sector, CHS addressing, early method for giving addresses, Wikipedia, great source. But you basically pick out, in our case, we're emulating a floppy, so we're picking out sectors of 512 bytes, which is what we start with, 16-bit real mode, all good stuff. We can choose to load or write to a specific, in this case, 512 byte sector on a specific head of our hard drive. So that's what we're going to do using int 13.2, stanislavs.org, good site. Also, Ralf Brown's Interrupt List, very good site, which gives more info. I just chose this because it was, bare minimal, so I can see everything on one page. But read disk sectors, you set it up by moving your numbers into your registers here. AH will be 2 for writing with Interrupt 13. AL is the number of sectors to read, to read the disk. Writing would be AH3, but we're AH2, so the number of sectors we want to read from the disk, in this case, will be an AL. Our track cylinder number, so what cylinder we want to use. In this case, will probably be 0, because we're just doing the first disk for everything. A sector number that we want to get goes into CL, a sector number that we want to read. So we read a certain number of sectors from the disk. If we just want to read the next sector after our first boot sector, because it is the first sector, in other words, the 512 bytes after our first loaded boot sector of 512 bytes, that would be sector 2, right? So, but we give it the number of sectors you want to read. If we just want to read one sector past the first one that we've loaded, then this would just be number 1, one sector to read. We'll probably do cylinder 0 because we're just starting from our boot disk, which will be 0, which is the drive number that's in DL as well. If you just start and boot up, this should be 0, although you can set it yourself just to be safe. It can also be 0x80 or 80 hex if you want to go by zero-based indexing for your drives. Otherwise, if you do 0 or 1 by themselves, it'll just count as like the old style of floppies and then the boot disk. And that's also why, your hard disk is C, traditionally C drive, because the A and B drives were for floppies. So that's, that's a bit of history for you. So that's nice. But yeah, number of sectors to read, we'll just start with 1. Track cylinder number will do 0. The sector number we want to read will be 2, because it will be the second sector, the first one being our boot sector. So CL, I think we'll set up as 2. DH is the head number, we're going to do 0, just to do our boot disk. Drive number should be 0, but we can reset it if we want to be safe. ESBX, now this is bringing into mind segmenting, which I have not gone over, which I'm going to butcher completely, but that's okay. But you have addressing and segmenting for memory that you're reading. By default, ES is like an extra segment register that you get in 16-bit real mode. You know, you have AX, BX, CX, and DX, your 4 general purpose registers. But there's also segment registers, which a segment is basically just like a partition of memory of our RAM. Or it could be other memory, I guess, but I think it's traditionally just RAM. But it's a part of memory that we're using, working memory. You can break it up into segments, and by default, our processor's doing that already with our code that we're running and executing. ES is a segment register, like AX through DX or general purpose registers. ES is a segment register, which you can use to load or go to or specify a specific segment of memory. So BX in this case, after the colon, a segment colon, and then, you know, another memory number, like say ES in this case is like hex 1000. So, you know, we're starting our segment at memory address 1000. BX is an offset into this segment. So, and I think at this point in 16-bit real mode, we can only specify up to 64-bit, well, not 64-bit, 16 bits or 64 kilobytes. If you do hex FFFF, whatever number that is in bytes is how much you can specify. And that's also corresponds to how big a segment, I think how big a segment is by default when we're starting in 16-bit real mode. But anyway, BX in this case, a segment colon, another memory number. So if BX was like hex 500, would be an offset into the segment contained within ES. And you're just going beyond, you start at the segment and then the offset goes further into memory from that segment. Your offset can be 0 and you're just taking the segment address for your memory, or your segment can be 0 and your offset can be the memory you're pointing to. So say ES was like hex 1000 and then BX was 0. The memory this is pointing to would be hex 1000 because it has a 0 for the offset. But you can also have the segment point to memory location 0, and then BX can point to hex 1000, and it would still be pointing to memory location 1000. But after you run this, AH is the status, which you can check status flags to see if you're successful or not. You can compare AL after this is ran with int13. You can compare AL again, which should be the number of sectors read. If this doesn't match the number of sectors you wanted to read, which you get by, like, you know, saving this somewhere before you run it. If the number of sectors actually read doesn't match the number of sectors you wanted to read, then you probably have a disk error and you should, you know, handle that accordingly. I think with actual floppies, it's recommended to keep repeatedly try to read the disk, maybe up to like 3 times, maybe more, just to be safe. But since we're emulating and bochs, BOCHS takes care of a bunch of stuff for us, we don't really have to do that at the moment. When we're running on actual hardware, which I do want to get to, probably not this episode, but running on actual hardware, we will probably want to take that into consideration if it does affect us, which it might. We'll see. I don't have actual floppies, but, you know, from a USB stick or something trying to emulate a floppy, we might need to repeatedly run disk checks and things so often. But we'll see. Anyway, you're probably bored of me talking to a blank white screen, so I'll probably get to it. CF here is a carry flag, by the way. It can, you know, it's part of the flags register, has to deal with statuses and things. But your carry flag will not be set. If your stuff was good, your carry flag will be set to 1 if there was an error. You can use that for error handling, but we'll get to it. We'll do a basic thing using these to read from the disk, and then we're gonna make our boot sector into a bootloader, you know, and load what really won't amount to, but what will amount to eventually, our OS, or like a basic kernel. So we'll get to that. Okay, so I'm back into here. I'm gonna make a separate thing like we did for our print string and our print hex. I'm gonna make another little utility thingamabobber. It'll be good. And I have some, you know, I have extra Emacs things because it's been a month since I last did this, but I have some special things to help me out that I'll probably forget how they work. But anyway, we're gonna make another little assembly file here. We're gonna call it DiskLoad.assembly.asm. So, and I have notes over here so I don't forget what I'm doing, which is awesome. But we're gonna call it DiskLoad, and what we're gonna do is, like in our print hex, we moved the hexadecimal string we wanted to print out as ASCII characters into register DX. So I'm gonna do that again, but with we're gonna set up the DX register with the amount, the number of sectors we want to read. And then also, I'm just going to automatically assume we're going to read past the first, for now. I'm going to assume we want to read past the first sector, so we're going to start at sector 2. But I'm going to move the number of sectors I want to read into DH, and then our drive will be in DL, because that'll need to be set up for our interrupt 13 AH2, our reading sectors from the disk interrupt that you saw. But I'm just going to call this DiskLoad. We're going to read DH sectors. And we're going to read them into our memory location. I guess I didn't explain that, did I? So our ESBX that we set up, sorry for not saying that. I'm a piece of garbage, aren't I? Switch back to this. Our ESBX, our pointer to the buffer, which I didn't explain. Basically, this is the memory location that we're going to read our sectors into. We're starting out on the disk, on our boot disk. And the first sector is our boot sector, of course. If we read additional data, past that, the sector after can be whatever, hello world, whatever. We want to read that into a location, into memory, which is what we're doing here. So the location in memory we're reading that code or that data into is this right here, ESBX, which is a pointer to a buffer, just a memory buffer. So hex 1000, say. We'll load our operating system into hex 1000. And RAM, so that we can jump to it and work with it. Otherwise, it's just sitting dormant on the disk, not doing anything. So this will go, we'll read the data from the sector on the head into this location in RAM in our memory. Now, if we were writing instead, I believe we have the sectors to write. We're writing to the disk from this location in memory. So we're starting at this location, and we would go, however many sectors starting at this location in memory, and we'd write them to the disk at this sector number and head number, track number, cylinder number, all that good stuff. That's how I think that works. I haven't messed with that too much yet, so I'm not going to say it's true or not, but I think that's how it works. But anyway, we're dealing with reading sectors. We'll go back here. Memory address, memory location from our drive DL. So our drive number, drive letter, what have you, drive number in this case, is going to be in DL, the sectors, the amount of sectors we want to read, whether we want to read 1, 2, 3, whatever, how many sectors, is going to be into DH, we're assuming, into this. I'm just going to call it DiskLoad. For our function we're going to call, we're just going to call it DiskLoad, so we can call DiskLoad after we've loaded the DX register with what we need, and then it should work. So now that we have everything, assuming in DX, we're going to push it so we can store it. We're going to store DX on the stack so we can check number of sectors actually read later. We can compare the number in DX or DH. DH will be the number of sectors actually read. Well, AL will be, but we can push DX and pop it back so we can compare it to AL after we read from the disk and see if we actually read the sectors that we wanted to read, or else we can do error handling, error monitoring, because we haven't read what we were supposed to in that case. But to set up our int13.2, our disk read function, we're going to move hexadecimal 2. But this sets up int13 AH equals 2 hex. BIOS read disk sectors. I'll just put into memory. Int 13. BIOS interrupts for, I think it's called like diskette functions, but I'm just going to put for disk functions. So that's all I'm going to do there. But AH is 2 to read the sectors in memory. DX, we're assuming DH would have the number of sectors we want. If you just access, assuming we've set up our DX register, or DH and DL, we can move the DH into AL, which will be a number of sectors we want to read. Number of sectors we want to read. For this case, I'm just going to do 1, because we're just going to go past the first, our first boot sector here. Into CH, which is either cylinder or the head. Which one is CH? Cylinder. We're going to move 0. So cylinder 0 and head 0 we're going to use, because we're just assuming our first boot disk is that our boot sector is contained on that we want to read past is in our disk that is booted. It's disk 0 in this case. It's our first one. So that's all that's doing. into DH just to make sure. We're going to move, well, we already got the number of sectors, but to set up for the read, we're going to move 0 into DH because that is the head number. So our cylinder 0 and our head 0 to signify our first disk. They're both 0 based. Sectors are 1 based though. I'll have to remind myself of that repeatedly because I'll probably forget. Into CL, we want to move the sector that we're starting at for reading. We want to start reading at the sector in CL, and we want to read the number of sectors contained in AH. So if we start at the sector after the boot sector would be sector 1 because sectors are 1 based. So we want to start reading at sector right after the boot sector. We want to start reading at sector 2. Start reading at CL sector. So we put sector 2 in this case, right after the boot sector. Right after our boot sector. And that should be all we need. Then we can call our interrupt here. This is also assuming we've set up an ESBX location in memory that we want to read to. Which I put up here. So we'll do that in our boot sector. We'll set up the ESBX memory location. We'll fill DH with the number of sectors we want to read, and we'll fill DL with the drive number, and then call this, and it should read into that location, and all be good. And funky-dory, hunky-dory, good stuff. So when you call interrupt 13, if you recall, the carry flag would be set 0. Well, it wouldn't be set, it'd be 0 if it's successful, or the carry flag would be set to 1 if we had an error. So you can get the result of this using a jump command, JC, which is jump. If the carry flag was set, it's nice, it's built in, so might as well use it. We're gonna have a little label we'll jump to called disk error. Just call it disk read error, I guess. Jump if disk read error carry flag set or equal 1. Carry flag set, carry flag equal 1 is what I mean by that little thing there. But if we don't go to error, carry flag 0, then we've read successfully and we can continue doing, whatever we want to do. We're good. So, assuming we read it successfully and we didn't jump to our disk error label, and our memory is now filled with our glorious sectors that have been read, we're going to pop DX back, restore it from the stack, restore DX from the stack. We can compare what's in DH, which originally was the number of sectors we wanted to read, with AL or ALDH. This can be in either order here. So originally, when we pushed it, DH equaled the sectors that we wanted to read. AL would be the set after you do interrupt 13 for AH2. AL will be the number of sectors actually read. So we get to compare the number of sectors we wanted to read with the sectors that were actually read. If they don't equal, then we didn't read the numbers that we wanted to. Well, the amount that we wanted to, so we have an error, so that's not good. If AL, which is number sectors actually read, not equal DH, can't touch type today, sectors we wanted to read, put number sectors, then that's not good and we want to error from that. So we can do a jump not equal and also go to our generic disk error label. Error. Sectors read. Even though I just put this out basically, I'm just gonna type it again. Sectors read not equal to number we wanted to read, and that's not good. But if we pass those, then we, passed everything. I'll just put return to caller. And all of our data was written to memory correctly. If it wasn't, we're just gonna make a little disk error thing, which all we're gonna do here is call our print string function pretty much. That's what we're gonna do, because it's useful. We have already written it, so we might as well use it. We'll move like an error message into here. I think my notes, I just put like disk error. So disk error message, we'll just call it. And then we called our thing print string still, so we're just gonna call print string. And then you can do a jump $sign to jump repeatedly to this area. Another thing I read, which, you don't know these things, they seem painfully obvious, of course, if you know some assembly, but I don't know, I haven't read assembly books. I don't know jack crap, diddly squat. But instead of doing this, I think another thing you could do is I don't know if I want to clear interrupts at the moment, but you can do clear interrupts, and then you can do halt, which is HLT, which will halt the CPU until an interrupt happens. And basically this can just cut down on CPU processing and resource usage. So we can use halt or CLI to clear interrupts and then halt instead of jump $, which will just keep jumping repeatedly using CPU cycles. We could do halt and cut down on those CPU cycles until I believe an interrupt is hit. If clear interrupts wasn't put, and then the CPU would, you know, spring back into action because it's awesome. But we're gonna, in this little disk error doohickey here, we're moving a disk error message, so we need to say what that is. I'm just gonna define bytes. I'm just gonna do generic disk read error. It's not good, so we'll just do that, 0. But that's pretty much all we need for DiskLoad, which is nice. Let's move our, I guess still the buffer here, right? Yeah, boot sect. Enter. Okay, still learning how that works. I do or whatever. I think it's called I do for Emacs, interactive do. It's pretty nice, I like it, but you know, still learning. So we're gonna call this thing from here, which, you know, the text is nice and continuated, so it's harder to read now, but this is our boot sector. We're gonna use our DiskLoad function within our boot sector. It's gonna be nice. We'll just include it with our other print files here. Include diskload.asm. So we want to load simple boot sector. We're gonna change, since we're loading stuff now, it's actually gonna be a bootloader. So this is actually now officially, after this is done, not right now, but you know, a bootloader, because we're loading our eventual OS. It's gonna be nice. Simple bootloader. And I switched caps lock and control. I have to keep remembering that for Emacs. Okay. I'll just call it simple bootloader. Yay. No, uses, I'll just put int 13 AH2 to read from disk into memory. And it'll load it as well, but that's okay. So we still want to start, we can still start at 7C00, that's okay. And when the boot sector is loaded up, this just dictates where in memory it should be located, which by default it's located there if you don't set up a jump to it to begin with, which is not an esoteric, which is an old, you know, thing that happens when you first boot up your computer. Technically, you're supposed to set up a jump to this point after you've loaded your stuff here to, you know, run your boot sector and your bootloader and things. Apparently part of this my numlock's on, okay. But we can just start here like we've been doing, that's fine. We still set the video mode, change the color palette. What we can do is move this stuff into something that we run into. Make an actual kernel and then load it. I guess we can do that. I might do that. Let me make sure this DiskLoad is right first. Which I have my shell buffer. Gotta have the LS. The LS and the CD, that's what you have to have all over, so you know you're coding master. People need to know you always remember your file names and don't LS every 2 seconds. Flash A so I can see everything. No, but anyway, that was a bad joke and that made no sense. I'm just gonna run phasm on our DiskLoad, make sure we're good. So undefined simple print string, that's good. Actually, I don't need to run phasm on this at all. What am I doing? If I run the assembler on it, it'll make a binary. I don't need to do that. What am I doing? I just need to include this because we're including the source, duh. Okay, I'm going crazy. All right, let's make a file that we'll do in a second. We're gonna call it, I don't even need to do touch. I can just open it in Emacs, right? We want to use our DiskLoad. We want to actually load something. So we want to make an actual bootloader. So let's load our kernel, or operating system. Well, if we're going to load something and we want it to be the second sector, I'm going to have to do something in a bit, which is concatenate the sectors together to make it count as like one single thing on the disk so that we can read from subsequent sectors after the boot sector. I'm talking over myself and making no sense. Anyway, we're going to make a separate file. I'm going to call it kernel.assembler. And confirm that, which I've had already from before. Wow, I didn't know Emacs saved the buffer, so I don't have to remember the work I did. Basically, I was checking if you could draw a square. I was learning graphics, so that's cool. That'll come up later. But anyway, I don't want this stuff. I want to learn, and by that I mean I want to type it out for you so I actually know what's going on. You know, Emacs save buffers like that. That's awesome. Everything's a buffer, everything's saved. But we're gonna make a little kernel thing, which all we're gonna do in the kernel is move our code here, just our set video mode. We're just gonna move all this stuff into the kernel so that we can load with our DiskLoad and do the same thing and just make sure that we're still working. That's all we're gonna do. So we're gonna load this, load the included files, except for DiskLoad at the moment because we don't need it. I didn't mean to press escape, to press P. We're gonna do that. I think Alt W saves that, yeah. And we're gonna put that all there, include files. So we do need to include DiskLoad. We do need the variables. The boot sector magic we don't need, but we can take this part. Take the Alt there, move it over. P. Wow, I cannot type today. I am obviously very tired, which is not great. That is all I wanted to do. Included files, our boot sector magic. See, what I'm doing this here, this won't be boot sector magic, this will be sector padding magic. Because we want to read additional full sectors, in this case, we're reading additional full sectors, which are 512 bytes. We're just gonna pad out this sector as well to 512 bytes. Our little kernel here. Which I'm just gonna call kernel.assembler. Basic, technically a kernel, I'll put it in quotes. Basic kernel loaded from our boot sector. Hooray! So that'll be cool. It'll do the same thing it did before. Make it blue, little skinny window, say testing and stuff. This jump here I'm going to change to a halt, because it'll cut down on CPU resource usage, which is great. I'll just put halt. The CPU. No, Control K kills the line, right? There we go. Man, it's hard to remember. Everything at work is literally like an acronym, and some things are a lot of keyboard shortcuts to get through menus and stuff, so my brain is like trying to keep that in working memory for work and then also try to remember these. And it's very painful, obviously, because I'm acting like I'm going crazy right now. But anyway, what are we doing? We're gonna load we want to load, let me save that first. We want to load, it was already saved, this into memory. This we're gonna put basically as the second sector after our boot sector, which I'll show how to do that. We'll do that in the shell after we're finished setting up the code to load it, actually. We have to set up the DX register for a DiskLoad thing, which I'll just set up the call right here, called DiskLoad, yay. Load, I'll just set this up first and then do the code before it. Loads our kernel into memory, and then we'll jump to wherever we loaded it to, you know, and that'll be nice. And we have to set up our ESBX. So let's do that. So let's do setup DX register for disk loading, sure, which will be DH and DL. So DH will be the number of sectors we want to load. In this case, I'm just going to load the kernel, which is 1. We're padding it out to 1 sector. So I'm going to move 1. I'll put again number of sectors we want to load into memory. And then in DL, we're going to move our drive number. So when you first boot up, DL should be 0 by default, but just to be sure and be safe, we can move 0 into it now. And for these, you can move in 0x or, 0h, because hex and decimal 0 through 9 are the same number, coincidentally. At least in this, it counts them as the same. But here we go. Drive number to load. I'm just going to put 0 equals boot disk. Technically, I think, in this case. But we'll just do that. So after we set up our DX register, which we did, we are going to set up ESBX, memory, address, segments, offset, to load sectors into. Gonna load our sectors into this point in memory, and then we'll jump to it and load it. So you can't move regular numbers into the segment registers. They're special. They're pretty awesome. The other segment registers, which I'm gonna just mention now offhand for no reason, I think are SS, which is the stack segment, which keeps hold of your stack in memory that you can set up. DS, data segment, which holds like variables and stuff like that. CS, which is your code segment, which is your area code here, your actual code, like org and move, like this actual text data, I think goes into the code segment whenever it's loaded, which has to do with, you know, the instruction pointer and other stuff that I don't fully remember. I kind of understand the concepts, but not well enough to explain, like everything else. I think those are the main three, and then ES is your extra segment, and then in 32-bit protected mode, you get a few extra segments that you want to work with, F and GS, and they're pretty nice guys as well. But anyway, set up our segment register with memory. You can't move normal numbers into the segment registers. So like, you know how you can move numbers into BX? Like we can move hex 1000 into BX. You can't do that with ES. It won't work. It just doesn't. It's overwritten, or the assembler won't like it, or the CPU just won't give a damn about it. So sorry for my French, but yeah, it won't. But you can move the address, the data contained within a general purpose register into a segment register. So we can move BX into ES, or another general purpose register into ES. We can say BX, it's fine, but we need to move something into BX first. I'm gonna move, like I said, 1000. We're gonna load sector to memory address hex 1000. And then we'll move BS into EX. So ES now equals hex 1000. And then into BX, we can do, we can do an offset of 1000. I guess that would be hex 2000, but I'm just going to move 0. So that ES BX would equal 0. So we can just load it into 1000. Alternatively, you could load ES with 0 and BX with hex 1000, I believe, and it would be the same thing pretty much, because memory's weird like that. But we're just going to do it like this, called DiskLoad. So this should load the second sector, our second sector 2, which we're going to put our kernel into memory address hex 1000. So after we jump, I think we can do jump to ESBX, but ESBX. But I guess to make it a little bit different, more clear, we're going to jump to, you can specify a memory address and, you know, your segments and your offset. You can specify it like this as a case to jump to, and it will do, I believe, a far jump. So it'll move your instruction pointer, and that's the thing, that your instruction pointer is basically a pointer that's running that your CPU is using in a register that says at what point in our code are we at. And then we need to execute the instruction at that point. So our instruction pointer, when we start, will be like, it'll point to here first, and then we'll execute this line. You know, 1 will be moved into DH, and we'll execute this. The instruction pointer will go on. I think you can mess with the instruction pointer if you want to be fancy with some things. I'm not doing that, not for a while yet. But anyway, when we do a far jump like this, called a far jump, I believe this is, it'll go to this location, and it'll move the instruction pointer to this location as well. And our data and code segments and everything else will be, you know, loaded at appropriate levels, or maybe they're all just loaded here. I don't remember exactly, but it'll jump to this point, which our kernel's going to be loaded into, say at 1000. And then our instruction pointer will point to this point now, and we'll start executing our code. So once we do this jump, and we jump to here, say, it'll load this code, and then we'll load this. And unless we have like a return, or if we don't do something like a jump and we jump back, which at this point our boot sector is at hex 7C00. So if we don't do a far jump back, then we will not go back to this point. Once we do this jump, we're over here, we won't go back ever, unless we have another jump back or something, or we load this into another area memory, jump to it, something like that. So that's pretty cool. Maybe it didn't make sense, probably not, but that's just how that works. Once we jump from here, this will be executed. We won't go back. It'll reach this halt and then stop, hopefully. But yeah, so hopefully this works, and we load our kernel at this point in memory. We actually load it, and it's great, and it works, and it'll all be good. I don't think we need anything else here, but I guess we'll find out, right? Won't we? We'll load the shell. Let's do our boot sector, since that's new. Undefined symbol, which is great because DiskLoad is including print string, which is good because I swear I did this before. Oh, I'm calling print string, but it's not included anywhere. Duh. That's why. We got to include it. I forgot I got rid of it. Duh. If we don't include it in anything, then it's not going to know what the heck you're talking about. And that is exactly what it was complaining about. it didn't know what the heck we were saying. So there we go, that works. We're also going to run it on our kernel, because the kernel is going to be made into a binary, which we have here, and we want to load the kernel. We want it to be as the second sector after our boot sector. I keep repeating, so hopefully I remember, and thus you remember, because I'll tell you. But how do we load other, in this case, we're just doing flat binary files for the moment. How do we load just our binary files one after the other to ensure that it is the second sector and not the first one, which our boot sector's at? Well, we can be basic Unix BIOSes and use cat, which actually works pretty well. Just put your arguments together and they will automatically be one after the other in the resulting file. So if we can concatenate our boot sector binary file and then our kernel binary file. They will be put into one file. In this case, if we cat them both, it'll just print the screen because we are not directing the output anywhere. By default, it just goes to your terminal, whatever you're running it in. But we're going to direct the output with our singular greater than sign, our caret here, whatever you want to call it. We're going to call our thing OS for the moment, just call it os.bin. So we're taking the result of putting this binary file combined with this one, which will be right after this one in memory. Well, in the resulting file, os.bin, and we'll be good to go. So now we have an os.bin. That's cool. So what we're going to do now is change we're going to load os.bin instead, because the first part of os.bin will be, and the part that will be loaded first is still this, our boot sector. It's just the kernel will be right after. And our boot sector will then take the kernel, which is in the second sector, which we have in our DiskLoad stuff. I saved that. DiskLoad. Taking the second sector, we only want to read one, which is what we're moving in. And it'll read it into this location of memory. It'll jump to it, and hopefully it'll run our code that is here, and we'll get the same blue box with the test strings. Hopefully that's all good and works. But we'll see. We will see. So we're going to load that into box source, just make sure everything's good. Okay, so box should load up this and load it all, and it should be good. We should see exactly what we ended on in the last episode. Hopefully. If it doesn't, then, I'll troubleshoot. Because we're great, and that's what we do. And we get garbage, so garbage is good. That's awesome. We do get the 12 AB, so we know that part is right. But the other parts are not right, because that should be the exact same, and it's not. So what did I do wrong? Where did I go wrong? Probably everywhere, because I don't do things well. Alright guys, so just getting back to this now, I spent a long time trying to pull out my hair and do different things to make this work. As usual, I overcomplicate things way too much. So I looked up some stuff online, some examples, and I decided to simplify what I'm doing here a lot, and then we'll go back and recomplicate it in the next ones. But this works at the moment. I just want to show what I did to make it work. I changed some stuff around. I might eventually move DiskLoad into its own thing. I just want to make sure this all worked first, as well as, the print string and the other stuff. They can be moved into their own files, of course. I just wanted to make sure this worked first before doing that off stream and testing some more. Anyway, what am I doing? So I'm setting up the ESPX, that's fine, for the DiskLoad. Set up the disk read. The head, 0. We're just doing this basic of the basics. Set up int13 AH2. The head's going to be 0. The drive's going to be 0. For our base boot drive here, the cylinder is going to be 0. The starting sector is 2 because we want to read after the boot disk. So I made a little read disk label here. We're going to read 2 disk sectors. Well, we're setting AH to 2 so that we read with the interrupt 13. We're going to read 1 sector, which is what this. Do number of sectors to read, yes. And then we call int 13. And if that didn't work and the carry flag is set, we'll just retry a couple times, and this usually works. If I have to do error handling, I'll add that back in. I took it out and have less to test for now. But then this is new. What I'm doing here, I don't know how much this helps, but I feel like it did, at least for a placebo effect, because this works now. So I'm just going with this. Since we're jumping to hex 1000, well, 1000 offset 0 ESPX. Just do ESPX equals... But since we're moving into there, I'm gonna set our segment registers in, in our memory. I'm gonna reset them up to 1000, which is where we're jumping to, and that might help with some memory things. It seemed like over here when I was loading it earlier and testing, debugging, there was just garbage memory in whatever I defined and tried to move into BX and things, and even SI, which I switched to. There's just garbage memory in there, so that was not working at all. But just setting up this, I think, may have tried to fix that, at least possibly for the data segment. Might have been the only thing that I needed to do. Extra segment, like these might be excessive. The stack segment, I might not have needed to do that, but at least the data segment I did, because that defines where things are defined in the code. So that makes sense for me, that resetting the data segment where this is supposed to be would enable this to be read at a correct offset when it's assembled. That makes sense to me. That's why we have to reset this, I believe. Anyway, then we do a far jump to it. We don't return, we, set up the boot sector. So this is what's loaded. We don't need any org. We can set like an org 0 or something here if we want, and it shouldn't mess anything up. But at the moment, I don't need it, and it works, so I'm not gonna worry about it. But, and I'll save it to make sure. We still do the video mode to change color palette to blue. I changed our print string here a little bit. I'm using SI, which there's a couple, I think they're index registers. SI is source index register and DI is destination index register. And there are some more interesting and complicated instructions you can use, like load and store string bytes or single bytes or however it was, like LODSB, if you ever seen that. Stuff like that uses SI and moves stuff into AL automatically, actually. So I might switch to that eventually, but as far as this right now, I'm using SI just to keep out of BX, because BX was not working whatever I did. So I'm using, registers that are made for moving stuff into. And traditionally, a lot of the time, people move their messages that they want to print into SI and do some fancy dancy stuff. But anyway, this works. So I'm using source index register with the test string in place of BX, which I was doing. So we're replacing BX with it and adding there for the print string. And then I'm halting, and this seems to work. It's very simple. I changed, the message here, but I'll show you. Again, make sure it works so that I'm not lying too much. I'm gonna remove if there's any binary files left, so I make sure I removed them. And then we'll compile them again, just to show you that, hey, it indeed works. Cat the binaries into our os.bin. Our box source is still using our os.bin, so let's load it. We should see, keep hitting keys. Should see, hey, kernel booted, welcome to Queso OS, which is awesome, because that was our message here. So we're good, we're working. It does look different. Go back to the kernel. It does look different. It is a lot simpler. I am going to remove, logic, print string logic and stuff out into their separate files and then retest it and debug it. I just wanted to get it to work first in a simple configuration to where memory was all right. And I think the main problem I was running into was this. I'm thinking now was not resetting the data segment so that it could see things properly. I think that's the main brunt of what was wrong, but just making sure you guys got what I found out. And this works. We now officially have a bootloader. Technically, maybe an operating system if we set up some kind of shell or interactivity and programs to load and run and stuff, then we might, have an operating system on our hands. And that's what I'm going to move towards in the next episode, the next few things, stuff for the future. I want to try to make a simple kind of operating system. And starting out, I'm still going to be extremely basic and easy, other than, moving this logic into its separate files. I want to maybe make a simple file browser, a file table, which I think is just, I'm just going to write file names in a sector to load them at, and then load them at that sector. Make a little screen to go through them, like a little menu. Try to figure out how to do that with graphics and pixels, maybe make a little, not a windowing system, but like a, a fancier looking screen, like, it says file browser and a title and stuff. I don't know, maybe we'll see. And then should allow the user to either go down and highlight the line, or just type a letter or something and then pick a program, pick a file to load in and jump to it and go back, stuff like that. And then I'd like to make this OS development as much as I can bootstrap itself. Run by itself on actual hardware, and then try to, develop the thing from itself. So eventually I'd like to do that, but until then, we'll keep going baby steps. I know I talk and ramble way too much, but that's what I'm doing. Just want to make sure this works, and it does. So I'm actually really happy about that, which is good because I always stay up way too late due to insomnia and other, you know, things in life. But anyway, I'm gonna go to bed because I'm tired. My voice is getting tired and shot. Other than this agua, which helps. But yeah, thank you all for watching. I know it's rambled on. This stuff takes too long, but I'm still learning as I go along. It takes me a while. It took me a while today to test and debug, but we have an actual bootloader now, not just a boot sector. Maybe we can make it a 2-stage bootloader where this other thing loads a bigger thing in our actual operating system. But right now I'm going to keep it like this. Just keep it as 1 sector. Although I can, you know, we can go however long we want to. We don't have to stop at 1. We can keep going. But we'll get to whatever we want to do on the next one when we get there. So hopefully it won't be too long between episodes. I know it was this time, but I've had a lot of life stuff going on. A lot. But we'll see. Things are looking up. I'm in a better mood lately, so I'll try to record more. Anyway, yeah, still rambling. Dang. Yeah. Thank you all for watching. Sincerely, I do appreciate it. I'll see you on the next one. We'll continue. Exciting stuff.